Let's talk about rockets, and I'm going to use these lectures from one of my previous classes. So let's look at a situation in which there's a rocket that's moving in this direction, and it's moving with the velocity v, and you're in an inertial frame of reference observing the rocket. And so let's say that again, inertial frames are frames that do not accelerate. So let's say that you're in an inertial frame which is at rest, and you're observing the rocket move towards the right. So initially the rocket is moving with velocity v and its mass is m, so the initial momentum of the rocket is mass times velocity. So now the rocket ejects a mass dm prime in a small amount of time dt, and then the velocity of the exhaust is v sub ex. Now the mass of the rocket is obviously reduced, its velocity is going to increase, so the mass is reduced by the mass of the exhaust dm prime, and then its velocity increases by dv. So this is therefore the rocket, the momentum of the rocket. So this is the total final momentum that we're looking at. This is the mass momentum of the rocket, and this is the momentum of the ejected mass. So it's dm prime multiplied by v minus v sub ex. So this is the velocity relative to the inertial frame. So when the exhaust is released, it obviously v sub ex is the velocity relative to the rocket. But if you're observing this from an inertial frame outside, which is at rest, the exhaust is obviously going to take the velocity of the rocket also. So its velocity relative to the inertial frame is going to be v minus v sub ex. So let's apply conservation of momentum. Assuming it's an isolated system, there are no external forces, you can apply conservation of momentum. So we're just going to set this equal to that. And so you'll see that several terms would cancel out. So mass times velocity cancels out, and then dm prime times v cancels out. And then this is the term that we're going to neglect because it's the product of two differentials. It's going to be a very small term, so we neglect this. And so we are left with a relatively simple equation. So now let's talk about a subtlety over here. So now dm prime is a positive quantity, right? But we need to write this in terms of the mass of the rocket. So let's say dm is the change in the mass of the rocket. So let's say that this is m final minus m initial, right? So this is going to be a negative quantity, right? Because m final, the mass of the rocket is reduced, right, when it loses mass. So m final is less than m initial. And so we're going to, because of this, dm prime is a negative quantity. But dm is a negative quantity. Dm prime is a positive quantity. So it is related to dm by this equation. Dm prime equals negative dm. And so this is just like what we're saying, that if dm prime is 10 kilograms, then it's negative of negative 10 kilograms, where this is the change in mass of the rocket, delta m, right? Delta m is negative. So if 10 kilograms is the mass of the ejected exhaust, then it must be equal to negative of the change in mass of the rocket. And so therefore we write dm prime as negative dm, and then we plug it into equation 1. So now we have an equation that we can further simplify. We have because in both sides the variable is the same. It's a mass, it's m over here and dm over here. But before that, let's divide over by dt, and so write it in terms of write the equation in terms of Newton's second law. So when you're and the reason we're doing that, because we have the equation of motion, or Newton's second law. So this is F net, let's say, on the rocket, right? It's m dv by dt is the dv by dt again is the acceleration of the rocket, right? So then the net force on the rocket, mv dot, so this is also v dot, same thing. So mv dot is the negative of m dot times v sub ex. So v sub ex is again the velocity of the exhaust, and m dot is dm by dt. m dot is dm by dt. So So then this is this quantity. So negative of m dot is the rate at which the rocket is ejecting its mass, and then this quantity is also called the thrust of the rocket, sometimes represented as r, and you can also represent this f sub th, whatever you prefer, but I think the convention is r. And so let's again start with this equation without the dt. We divide it over by dt just to bring it in the form of Newton's second law to see what's going on with the net force. But let's further simplify this with just the masses. So let's get rid of dt again and divide over by m. So we have a differential an equation that we can further simplify by integrating. So let's integrate this equation from some mass, initial mass m naught to m, and then from some initial velocity v naught to v. And so when you integrate this, I'm just flipping over the equation. So you get v minus v naught. This is just integral of dv. And then remember the integral of dx over x. Let's say from x naught to x is just log of x divided by x naught. And so we get that. And so we have an equation for the velocity of the rocket in terms of its initial mass, the final mass, and these obviously, this is the initial velocity of the rocket, this is the velocity of the exhaust, these two are constants. And so because of so now this initial mass is the mass of the fuel plus payload. And if you might know how rockets usually work, they're multi-stage rockets. They release a payload at different stages, and it's because of this dependence on the mass, on this ratio of initial mass divided by final mass, that the engineers have built multi-stage rockets.